Okay, we'll work through the solution to quiz 8 in statics. So we have a beam that is supported by a pin connection on, well, this is a pin connection on B, and this one is kind of a sliding connection where we can get a normal reaction. So we'll have a normal force that's acting through that pin perpendicular to this surface. And at B we can have a reaction force in the y direction. Oh, this is B in the y direction, and a reaction force in the x direction. We also have a distributed load here in the middle. That's our only loading, and this side on the right, on the left, excuse me, where A is a 3-4-5 triangle providing that incline here. So there we have that 3-4-5 triangle. So what's our approach? Step 1, draw a free body diagram. Oh, FBD. 2, find the equivalent load. Point load. Step 3, we'll write equations of equilibrium. And then step 4, we'll solve for unknowns. Alright, so step 1, we'll draw our free body diagram. So we have our beam here. So if I can draw a decent beam. We have our FBY acting there, FBX acting there. Those are our reaction forces. We have some reaction force here, FA, and I'll just call it normal NA. Excuse me. Let me get that. So I need get rid of that. So I'm going to call that NA, acting in that normal to this 3-4-5 direction. And then we have a resultant force here, FR, that's the result of our distributed load. So there's our free body diagram. We get 2 points for that. Now, let's see what we have for that. We'll solve for that equivalent point load. So that's step 1. Step 2, we're going to have, it's the area under this curve, right? So we could take an integration of this, or we can just use our normal geometric identities. So it's going to be the area under that curve is the area of a triangle. Oh, area of a triangle. We have 1/2 base times height, so we're going to get 3 meters times 400 newtons per meter times 1/2. For this left side, we get the same thing for the other side, so I'm just going to multiply that by 2. So we're going to get, those will cancel out, and we get 1200 newtons, because our meter will cancel out with our newtons per meter. So that's our FR, 1200 newtons down. And now we can write our equations of equilibrium. So we're going to have step 3. What do we have first? Let's take a moment. We're going to sum up the moments around B. We're going to have to equal 0. What do we have creating a moment around B? Well, we have our resultant force here. Is acting down. That's creating a moment this way around B. A is pointing up and to the left. That's creating another moment around B. I'll call it MB due to normal A. This one was MB due to resultant force. And those two have to equal 0. So that will get us our vertical component of A. So that's going to be equals 1200 newtons times 3 meters minus 6 meters times NA in the y direction. equals 0. So we have 6 meters NAY equals, oh, not 18, 3,600 Newton meters. So NAY equals 600 newtons. That's part of it. And we get 1 point for this equation of equilibrium there. Alright, so we have that part. Now let's do our equations around the equilibrium equation in y direction has to equal 0. So what do we have there? We have plus 600 newtons from normal part of A, minus 1200 newtons, plus FBY, all equals 0. So we'll move this 1200 to this side, that makes it positive, subtract 600 from that, so we'll get 600 newtons equals FBY. So we get 1 point for this guy. I think we're getting 1 point for each of the solutions, is that right? Oh, 5 points total for the numerical solutions. And then we can do the sum of the forces in x equals 0. So what do we have in the x direction? We have FAX, so that normal, let's call it the normal part force at A in the x direction, plus FBX equals 0. We also, this is where that 3, 4, 5 triangle comes in. So let's take a look a little more carefully here at this 3, 4, 5 triangle. So if we know that this force is normal to that triangle, it's going to be acting somewhat out this direction, approximately. So if this was, if I draw a horizontal line here, oh, that didn't work so well. So if that's 3, 4, 5 this way, to rotate that 90 degrees basically is what we're doing, right? So we're taking this leg here and rotating 90 degrees, and that becomes this leg here. This leg here rotates and becomes here, and this one, the hypotenuse, stays that. So our vertical component is NA in the y direction equals 4/5 NA. NA in the x direction equals 3/5 NA. So we can use that in our equation down here. I already found the NA in the y direction, so that was 4/5 NA equals 600 newtons. So NA, scroll down, NA then is 750 newtons, so dividing that by 5, multiplying that by 5 and dividing by 4 gets us 750. That's that normal force. So here in the x direction we'll have 3/5 times 750 newtons plus BX equals 0. So dividing 750 by 5 gets us 150. Multiplying that by 3 is 450. So this is 450 newtons plus FBX equals 0. So look at the FBX on that side. Equals negative 450 newtons. So that's going in the direction to the left there. So here we have this part, the y component. So we get 1 for that, 1 for this. If we have these separate, we have this, we have our a normal in the y direction, that gets us 1. And what am I missing? 1, 2, 3, 4. I think I had one more here. 450, 750, 750 by 450, 600, 600. Maybe that's what I was missing. No, 1, 2, 3, 4. Oh, I had my FAX. The normal in x direction was 450 newtons. So I gives you 1 there as well. If you had your other numbers correct, I would accept that. So we have 1 point for each equation of equilibrium. So 1 there, 1 here, 1 here. 5 points for the correct answers there, and 2 points for that free body diagram gets us our 10 points. And that makes sense, right? That this x component has to be going this way, since obviously this A component has to be going to the right, the B component has to be going to the left, and since it's centered here, our forces are going to be equal to match that normal, the downward force of our distributed load, and they'll have to be equal to each other since it's located in the center here, so our moments are 0. So that wraps up the solution to quiz 8.